Okay, it's been a while since my previous recording. Um, and because of that, and I guess also because I've been thinking about other things, I thought I would talk about something else as opposed to my previous problem, which was about this divisibility of the sums of the orders of the cyclic group. Um, and I came across this problem that someone asked on Reddit, and I actually forgot the exact problem, but it had to do with tournaments, which one can think of as starting off with a complete graph and assigning an orientation to the edges. And so I wanted to study these tournaments, see if we can ask some particular questions about them. I guess sort of one maybe obvious thing that one could do is look at the amount of different tournaments. Look at different tournaments and look at some properties, assign some combinatorial invariant to them, and then try to find if there's like a nice generating function. So that was one of the things I wanted to try, and just mess around a little bit to see what happens. And since graphs are always just nice objects, I was expecting that I would at least make enough progress. So let's have a look. All right, so maybe just as a warm-up, let's write down a complete graph on 3 vertices and assign an orientation. So we could have something like this. And let's just for good measure write down all of them. Oh, okay. Yeah. Okay, I started. So let's finish it, I guess. Okay. Actually, yeah, let me just write them down for a little bit larger. Okay, I mean, maybe the first silly observation to make that for a fixed n, where n is the number of vertices in the graph, the number of tournaments is given by 2 to the power n squared minus 1 over 2. We're assigning an orientation, and there's exactly this many number of edges, so that makes sense. Let's see. Well, okay. Let's see if we want to have any hope of there being a nice generating function. Then we would want this number. Let's call this a sub n, the number of such tournaments. We want to see if a sub n times x to the power n has a nice form. Let's see. I'm actually not sure what that is equal to, right? Because this is a little bit has quadratic exponential growth. So let me just pull up mathematica. Okay, let's wait until mathematica starts up. Okay. Okay, so we have this guy. I hate this screen. It's way too bright. So we have this quantity, and let me just write it like this because why not? X to the n All right. Okay. It doesn't want to simplify that. Wonder if it just has to do with the fact that it might think x might be. It didn't specify anything about x. Um, oh, of course. This doesn't converge nicely because of. I mean, the x to the n cannot really compensate for the exponential growth or the w exponential growth. That makes sense. Okay. Let me see if we just sort of try to put a factorial here that changes things. Okay, this doesn't have a nice expression. That's good to know. Okay, well that already tells us that our initial attempt um, tried to find a generating function that includes more data. Um, some other combinatorial properties is also hopeless. Okay, so that's a bad try. Um, let's have a quick look though. Lambert series. Is this useful by any chance? No, this does not seem to be useful. Okay, that's a bit of a bummer. Okay. Um, okay, that's annoying. Um, okay, well then let's see what other kind of questions we can ask. Okay, so this is definitely not going to work. Um, so I remember the question on Reddit had something to do with given a graph like this and you assign some orientation to them, um, then how many of them have a unique vertex that has the maximum number of outgoing edges? Or incoming edges, doesn't matter, of course. Yes, that doesn't matter. So let's just have a look. Of course, I can always have a construction like this, right, where I have one edge that has the maximum number of outgoing ones. And if that happens, then it necessarily needs to be the unique maximum one, because when we assign it, I mean, every other vertex has at least one incoming edge into it, namely the one that we just started drawing lines from. So then it is unique, and of course there's n, as many as n of those. Now let's see if we, so okay, let's write this down as observation. Let's see, let's call a vertex, let's call the out degree. Let's call that, well, that's just the out degree. So we can choose n minus one edges, and there's exactly, let's see. Okay, so let's say we fix a vertex v and then we assign n minus one outgoing edges, then we are free to change the edges as we want for the other ones that we didn't assign yet. Well, how many options are there for those? Well, that's just the complete graph on n minus one vertices. Let's quickly check. Yes, okay, so then we just, what is this? We just got this quantity here by 2. Let's quickly expand this, n squared. Plus 2 plus 1 3n. Yes, that should be right. That should be right. And divided by 2, of course. Okay. So let's see. This, and then of course there's n choices for this degree that we, for this vertex that we choose. And this, let me see. Yes, this should, I just want to sort of count the cases, and I just want to make sure that I won't be over counting later on when I go to more complicated settings. So, okay, these are the number of options such that the out degree, the maximum out degree, let's call that a champion, why not? If a champion has odd degree n-1, then it's necessarily the unique one. There's n choices for it, and then for each of them, we have this many options. Okay, that is sort of nice, I guess. Oh, of course, sorry. It's 2 to the power, this number. Yes, okay. This is sort of nice because if I just look at the total number of options, then it's, I mean, okay, I guess that this proportion still vanishes for large n. It should vanish, I believe. Okay, I guess that's an interesting statement, right? We can ask, okay, I guess we could ask how many champions there are, because the champion might not be unique. It is unique in this case, when the out degree is n-1. But if the, let's see, yes, we can ask for the number of champions. How's that sort of distributed, right? If I just give you a random tournament, how many champions are there on average? And let's see. And what is the maximum out degree for the champions? Now, thinking about this, I think that this is rather easy to do, because we can sort of split the problem up nicely. Like for each vertex, we can ask, okay, for each of the edges connected to the other ones, we can assign either outgoing or incoming. So that tells you that the and all these choices can be made independently. So as maybe an example, I say maybe I'm going to start here. I'm going to assign this orientation to the edges. Then great. Then I still have the remaining then complete graph, and then I can say for this one, oh, there's I see. Okay. So for our first choice, in this case, we had assignments of 3 edges, which has fixes something about the out degree and the in degree of the vertex, this vertex that we start off with here, V. But it also says something about all the other in and out degrees of these other vertices, right? Because this guy here, for example, gets 1 incoming edge from here. So let's think of this as follows. So, okay, I guess one thing that I want to do, like a nicer quantity to look at, is not the out degree and the in degree sort of separately, but look at the, let's see, what is nice. Let's calculate the in degree as +1. Oh, that might be a little bit annoying if I, okay, sure, let's stick with that. That seems nicer. Like the incoming edges, they count as +1, and all the outgoing edges count as -1. So what does that mean? Well, I can think of this assignment as a Hmm. I choose a sequence of pluses and minus ones that I assign. Okay, let's write this out formally. We're going to start with some ordering v1, v2, vn. Then for we're gonna just let me use sort of algorithmic notation. We're gonna set I equals to 1, and then we're gonna look at vi. Then we are going to have some function or some assignment. Um, let's see. I want to have some function. Let's call it f sub I that takes in v minus. So here we're going to subtract all the previous vertices, vi minus 1. Is that correct? I want to subtract vi as well. Vi minus 1, vi minus 2, etc. This is terrible notation, of course. This is a function fi from this subset of the vertex set to, let's see, um, hmm, oh, okay, this is just going to be plus or minus 1. Yes, silly. Okay, and so this is an arbitrary such function, which we can think of as our assignment. Then what we're going to do is mhm. Okay, so these are the functions, these are the assignments, and then the thing that keeps track of what I want. It's not very nice mathematically. I mean, this is a clear algorithm, or not so much an algorithm, it just constructs an assignment. Let's see. Okay, let's take a step back. I don't think this is the right approach. Let's assume that I start. Um, I'm going to fix the number of champions. Um, let's say I want there to be at most one champion. Okay. One option is, as before, that um, one of the vertices has exactly n minus one outgoing edges, and then necessarily we know that this needs to be the unique such um, that it needs to be the unique champion. That is nice. But what happens if, for example, it's n minus 2? So um, I'm not sure if n is 4 is big enough, but one thing that we could have is something like this, like this. This needs to go like this. And I want to have another one that has 2 outgoing ones. So that is easy. I need to have this and this. And then there's some choice here. Yes, let's see it like this. Let's see. So this one has two outgoing, this one has two outgoing, this one has one outgoing, and this one has one outgoing. Okay, that's good. Now there's exactly two of them. Which is good. And of course, we can consider rotations. Um, what happens if we do something like, let's see. Oh, I'm not sure how I had this one oriented. Let's see. Yes. If I now do this one has two outgoing. This one has two outgoing. This one has two outgoing. Uh, oh, but now this one has three incoming. Okay, that is interesting. Okay. Okay, so by relaxing it from n-1 to n-2, we can have three of them, which honestly, it's a little bit surprising. Um, I guess that doesn't make that's not too. Okay, I guess that is okay. Hmm. I feel like this is a problem that should sort of naturally split in the sense that you can do the edge assignment vertex by vertex and then sort of do a um, um, do sort of recursively to see what would happen. But okay, actually, yes. Um, okay, let's use an ordering 1, 2, 3, 4, etc. Then we can think of our objects as, for the first vertex, we don't make any choice. Then for the second vertex, we think of it, okay, making a choice. Um, um, so I'm still trying to think of this from a generating function approach, with the hope then that even though the generating function might not nicely converge, we can maybe still use a purely use it as a purely formal expression, and then maybe ask Mathematica to still expand some of this stuff. Um, yes, let's see. So I guess sort of what I wanted to do here before, I guess around here, I started with the large graph and then I started taking vertices off and then break it smaller. But it might be more natural to sort of build up the graph as we go along. All right, so we started with this, then there's no choice here. Then for the next graph, for next vertex, we can think of it as, okay, we assign either this edge or this edge to it. And then for the next one, so we make a choice here, which is just empty set. There's no choice there. I guess singleton, I guess. Then there's no choice here. Sorry, there's a choice here, namely just between uh, ingoing or outgoing. Then for the next graph, independent of what we put here, whether we put ingoing or outgoing, uh, For the next vertex, we can make this choice of like either here, right? We make the choice of orientation. And so I can really think of it as a sequence of bit strings, where the length of the bit string tells you from the current vertex, add a go either let me see, what will be a good convention? Let's use -1 for outgoing and +1 for incoming. Um, hmm, but there's just something nice about constructing it this way. Well, if I add a bit string, yeah, the annoying thing is with this maximum is that we are yeah, maximums don't really play nice with generating functions in the first place. Okay, let's see. Okay, maybe one question. Okay, I guess this is a bit of a boring question, actually. Or at least, okay. One can ask what kind of sequences of out and in degrees are possible, because as we see, it's not possible to have all degrees going out. Hmm. Let's see. Um, okay, no, I don't know. Okay, this problem seemed a little bit more tough than I thought. Okay, let's pivot completely, and let's say I take a tournament like this. And I guess one could ask it for more general graphs, but let's say sort of simplistic. And I now define an algebraic operation on such graphs where I choose a vertex, and then for each vertex, I'm going to change the orientation of the outgoing edges. Um, let's see. Now, I guess a very natural question to ask is, can we go, if I specify two graphs, can you check efficiently whether you can go from one to the other using these uh, these operations? Let's call these orientation reversal. Let's just call them reversals, I guess. That might conflict with some previous terminologies, but whatever. Okay, I mean, every time you have a question like this, can I go from one thing to the other? Then I guess the natural question to ask is whether a sort of greedy approach works. And actually, let's see. I think this operation is commutative. Let's see. Yeah, it should be commutative. Okay, yes, one way to think about it is as follows, and I think this also generalizes. Choose an arbitrary orientation of your edges, like this here, and call that 0. Sorry, let's think of it like this. Um, we consider the edge set as a vector space, and then we call this the 0. And the idea is if we change the orientation of one of the edges, then that corresponds to a 1. So let's maybe make that more concrete for a slightly smaller example. So I have this. Let's say this is my initial configuration. Then I call this a, let's see. Then I assign, so let's say this is edge 1, edge 2, edge 3. Then if I just write this down as standard Rn notation, this is corresponds to 0, 0, 0. If I now do a reversal on 3, then I change this orientation and I change this orientation, which just gives me yes, okay, which just gives me this. Now, right, so I can sort of represent these reversals as binary vectors. And in fact, they form a vector space because, well, sort of this picture already makes it clear that it's commutative, and also that they're involutions, which is clear. But if we have an involution set of operators that form involutions and they commute, and well, we have n of them, right? Then we could think of this as a vector subspace over f to n. And in fact, if we look at the set of the vector space of all edges, then this is a subspace of it. And what is the associated vector space? Well, for each, let's see, so it's spanned by exactly this guy, right? We have, no, sorry, this is incorrect. Wait, is this correct? No, this is incorrect. I think this is called the incidence matrix, where you have your V1, your V2, etc. And here you have the edges that are sort of incident on that, and then you put a 0 if they're not incident and 1 if they are. Right, so you just get to hear some binary matrix. And every time we flip some VI, then we do reversal on VI. We change the edges of that are sort of incident on VI. So this tells you that the vector space spanned by the incidence matrix, or the rows of the vector of the incidence matrix, is exactly the vector space under consideration here. And so what does this mean? Well, you can take two different graphs, look at their representation in this vector space, you subtract them from each other, or add them since we're working modulo 2. And then the question is this vector then in the space spanned by these rows of the instance matrix? And the answer is, okay, yes, you can check this rather quickly, because you can just do Gaussian elimination to check whether element is in your subspace. Um, and this should still, let me double check. So this should be, for a standard matrix, I believe that this is uh, order n cubed, where I believe n is the largest dimension of your matrix. But of course, here we have n vertices, while here we have n order n squared. But that's still fine because this just tells you that this just becomes order n to the 6, which is not nice, but it's still efficient. So one can efficiently decide this. Okay, that is, I guess, a little bit more boring than I had hoped for. One really sees how strong this commutative and I guess also this involutive property is. Now, of course, this was for a general matrix. Sorry, this was not for a general matrix. This was for the instance matrix of the complete graph. Let's have a quick look at the incidence matrix. And let's see what kind of properties we can find. Okay, let's just quickly double check this example here. One should be connected with one with, yes, that checks out. Two is connected just with one. Yeah, okay. So this is exactly what I said. Okay. Here there's also the instance matrix of a directed graph. Okay, I guess this is exactly the structure that we wanted to have, in the sense that if I give you the incidence matrix, then summing the rows, the row of a given vertex, tells you sort of the net in slash out degree. Okay, this is also good to see. I'm not the only one who thinks about this. Okay. Okay, this seems interesting. Okay, is equal to the null space. Okay, yeah, I guess this makes sense. Okay, let me see. Is there anything else we can say? Okay, it doesn't really seem like it. Okay, I think here is maybe a good time to stop. If I figure out how to do this. Okay, I guess I'll just end the call. Oh, okay, I guess how do I do that again? Okay, here we go.